Hi, I'm Soundarya. Let's start with supervised learning and prediction. Supervised learning is a machine learning approach where models are trained using historical data with known inputs and outputs. The aim is to learn the relationship between them and make predictions on new data. Prediction is a type of supervised learning where the output is a continuous value such as sales or electricity consumption. For example, past electricity usage can be used to predict future demand. Coming to the second question, the regression plays an important role in business decision making. It helps organization predict demand, plan production, and manage inventory. A real-world example is the beer consumption dataset from Australia, where regression models were used to forecast future beer sales, understand seasonal effects, and support inventory planning. There are several popular prediction techniques. So, the linear regression models is a simple linear relationship. Neural networks handle complex non-linear patterns. Support vector machines predict continuous values with an acceptable error margin. Regression trees and random forest split data into subsets and combine multiple models to improve accuracy, such as in electricity consumption prediction. Coming to time series analysis, it focuses on data collected over time, where past values influence future values. As a time series consists of a trend, seasonality, and random noise. In the beer dataset, HTL decomposition was used to separate these components and improve forecasting. For time series prediction, the Holt-Winters method models uh, trend and seasonality using exponential smoothing and achieved a MAP of 5.4 percentage on beer data. Another common method is ARIMA, which uses past values differencing and past errors. Finally, prediction quality is measured using the error metrics such as mean absolute percentage error or MAP, which calculates the average percentage difference between actual and predicted values. Here is the formula of MAP.
Chistia. Here in Bayesian trigonometric regression, we are getting 1.97 MAP for a single annual cycle. So if we consider two seasonal cycle with an extra wave, so the accurate calculation will be more accurate, and the error will be 1.35 almost from 1.97. So we may consider two cycle. And for hot winter exponential smoothing to handle both trend and seasonality. As beer seasonality scales with consume level. So if we consider a multiplicative instead of additive seasonality, we will get better result, which will be 3.8% instead of 5.4. So for ERIMA, if we consider seasonal ERIMA for seasonal consolidation, so if we will get after we will get 3.8% instead of 5.4. So this is our calculation summary, which is.
Hi, let's check out the prediction of electricity demand. Here we have loaded the CSV file dataset using pandas, and the dataset does not have the headers, so we named it, and it contains 7 columns where R1 to R6 represent the previous 6 hours of electricity consumption, and target R7 is the value we aim to predict. After loading the data, we inspect the first few rows and check the data set structure. Moving to the data overview, like the data contains 1,39,571 records and some numerical features. Let's discuss the descriptive statistics. Here, the average electricity consumption across all hours is around 280 kilowatts, and this value remains consistent across input and target variables. The median is slightly higher than the mean, indicating a small left skew in the data distribution. The standard deviation is approximately 129 kilowatts, showing significant variation in electricity demand. Consumption ranges from 9.5 kilowatts during the low demand periods to over 765 kilowatts at peak demand, highlighting the need for the robust regression models. Overall, the dataset is clean, well structured.
Hi, I'm Chistia. Now we are going to describe the exploratory data analysis. So here in the correlation metric, we see adjacent two hours have a very strong positive correlations. And this is a time series data. The distance past hour have weakest relationship. The strong linear relationship suggests that the linear regression should perform well as a baseline. Now we see the distribution of target electricity load. So the distribution is not normal. the data varies significantly during the night and day and nights and the weekends. So the graph is skewed literally at a left. So it suggests that while average consumption is to 80 kilowatt, there are distinct periods with very low consumption and likely in a deep nights. Okay, so uh, here we see the two clusters. One is 100 to 150 kilowatt, and which is considered a base load, and another is 300 to 400 kilowatt, which can be considered a peak load. So this means a utility company should consider plans for peak to meet at the high demand, the right side, and might be efficient for the low demand periods and the left side. So here the line graph shows the continuity and a smooth transition. So that means that there is no massive change. There is no massive change from one to next hour. So there's a steady increase and also a steady decrease, and there is also some flat periods, relative constants. So we have captured a blocks here also, and we got 13 duplicate records, we can remove them, but we have found 21 outliers, so we will not remove them because extreme high values are often real and crucial. So if we remove them, our model might not learn to predict extreme high loads, so we are not going to remove them. Here the data, we are considering the data for 80% for training and 10% for validation testing. We use the 10% for tune our hyperparameters, so that the model might not be overfitting, and 10% for testing. Thank you.
Myself Jayanta, and I will explain the 6 different regression algorithm we have implemented. So first one, we have implemented logistic linear regression and elastic net regression. So it is a simple linear regression, and here we can see the performance of that regression, and here we can see the MAPE is 11.93%, and in the total elastic net regression the MAP is exactly same. Now why this is happening? Because let's understand what is elastic net regression. So elastic net regression is a regression where many regularization applied, like lasso and ridge, but as the data don't have any multicollinearity or anything, that's why these results are similar or identical of each other. Then we have compared random forest regression and support vector machine. So what it is doing, so if we see the SVR, its MAP is so high, so it is failed completely, and in random forest regression the MAP is 10.79, so it is slightly better than linear regression. Now why this SVR is failing? It is mainly failing because of the it cannot find the meaningful patterns because of the magnitude problem, because the distance, the squares between similar hours is too high, so it is completely different. But in the random forest it is just is load greater than 300, this kind of rule based segregation, that's why it can do better than sphere. Now let's do a neural network 1 layer and 3 layer analysis. So if we see the both of this, so in 1 layer analysis is a simple one, still we have 11.03, and the 3 layer combination we have 10.66, and this is the best among all of this algorithm with the 3 layer of. And here you can see the input layer is as it is, and in the middle layer we have used ReLU. And here the explanation actually why this is happening, the neural network 3 layer. So let's understand the weight and bias and everything. So if we see this histogram of weight values, so we can see all the weight values peak is close to 0, so we can say this is a very strong and significant model, and it is a stable model. That's why the weight distribution is maximum value is in 6. And here we can see the feature 5, or the 0th hour has the first hour has the most important, and this hour has the lowest importance. So now let's talk about some business finding. So what is it? So here we see the highest positive weight we can see in first hour. So what does it mean? It means we have a significant time to be prepared. So a business owner or a power company can prepare for upcoming peak or anything from 10 hour 6 hour behind. So And the correlation strategy, if we see there is a negative one for hour 3, so what is it? It is a kind of false alarm. So if in hour 3 there is a hike, don't be panicked, don't put everything, it will solve. Then the last hour, the just before the targeted hour, there we see there is zero errors, so it is a noise. So if there is a hike, don't worry, it will solve. So here is the summary of our analysis. So fast hour as a business term, ramp up cheap power. So start heavy coal turbine to be ready for when it is exactly needed before 6 hour before. The middle hour, it is kind of inverse relationship. If it is high, it will solve. And the last hour, the 6 hour, it is a noise. Don't panic and buy expensive thing to solve this problem. Thank you.